Okay, so today's lecture is on color correction. So we have seen last day we saw how we perceive colors, and then now we will study how to operate with those colors. So that is something that we already know. That is that color is a vector. So we have presented it as a combination of three intensities: the red, green, and blue. So if you have a vector, let's go to the whiteboard. So have an image. So you have an image, and then you have the pixels, and then one of those pixels we have say RG in vector. It belongs to 0 to 55 Q. So we have a number between 0 to 55, and for each one of the channels, and the combination of those intensities are our colors. Okay, so we will operate with these vectors to transform colors, one color into another color. That is what we do. So colors are, as I said, vectors in this RGB space. So when you have at a particular point you have this vector 185, 95, 12, what you mean is that the red should go to 184, green to 95, blue to 12, and 0 is black, so 0 intensity, 255 is maximum intensity, that is white. So if you put 255 to 55 to 255, you get white. You put 0, 0, 0, you get black. And then depending on how much intensity you put in each one of the channels, you will get one color or another. So you can think, as it is a vector, you can think of the color as a traveling instructions. So when you have 184 in red, what it is telling you is if you want to reach your point, your color, in this color space, you have to travel 184 units in the red direction. And once you have reached this point from the origin, you reach this point, now you have to travel 95 in the green direction, that is this one. And then you have to travel 12 in the blue direction, and then you reach the color. So a vector is nothing more than traveling instructions. And then you can use also this notation where you are using more a kind of vector notation. So you have unit vectors in the direction of red, green, and blue. But this is like x, y, z, but now they're called red, green, blue. And then the coefficient in front is how much you have to travel in that direction to reach the point you need. Okay, then, so if you have three numbers of 256 possible values from 0 to 255, then you have 16 million colors. Those are the colors that you can express with 8 bits. Okay, then we may have this color axis. So the origin is here. As you may remember, 0, 0, 0 is black. And then we have the red axis, we have the green axis, the blue axis, and here we have the words. Okay? And this is our 3 vectors. So this 3D coordinate system, the red, green, and blue. But you may define that coordinate system. So you may define another coordinate system like this one. And this one is cyan, yellow, magenta, which are the diagonals of these sides of the cube. And actually, we saw the other day that this red, green, blue coordinate system is very much used when you have a display like a TV or a computer. And cyan, yellow, magenta is the one that you use when you print. So when you print, you use this coordinate axis rather than the red, green, and blue. But anyway, it is just a coordinate system, so you don't care. You can express any color in both coordinate systems. Okay, then this is just to highlight that idea. So if I have this point in the red, green, blue coordinate system. It has some coordinates. But the same point in the cyan, magenta, yellow, it has different coordinates. You reach the same point, but now your coordinates are different. So your coordinates really go with the basics that you're using. If you're using the red, green, blue, then the coordinates, they multiply the red, green, blue unit vectors. While if you're using the cyan, magenta, yellow, and your coordinates, they multiply the cyan, magenta, yellow unit vectors. Okay, then, yeah, so what we will see is you have some image, and then you want to transform it in some way. So you can make it more red, more green, more blue, more yellow. So we will transform the colors to have different versions of this image. Okay, so let's say that I have this image. I have this histogram of the 3 channels RGB. And yeah, so the histogram of the image. Good. Now I apply just to the red channel. I apply a gamma transformation with factor 2. So you may remember the gamma transformation. Gamma transformation was something like this. Was something like this. So if you have x, so x on the region, and then you have x divided by 255, 1 I think it was something like that. Check exactly, don't remember exactly this one. I think it is this one, but it could be down. So check it out the previous one. I think it was the second lecture or something like that. So the idea is you take your color, you scale it to be between 0 and 1, and then you do a gamma correction. And you have to take it back to the original scale. You have to multiply by 2. Okay, then we apply gamma equal 2, and because gamma equal 2 is only applied to the red, not to the other 2 channels, then only the red histogram changes. And this we already know why we are getting holes in this histogram. So these holes are coming from an expansion of the contrast. So that there are some values in the output that are not mapped by any color in the input. And we also know why we have these spikes. So these spikes are coming because 2 colors in their input, they are collapsing into the same output color. And then gamma equal 2 shifts the whole channel to the right, so the image is now more red. But you can do also gamma equals 0.5. So if you do gamma equals 0.5, then you're compressing the histogram in the other direction, and then making it more cyan. Okay, so in this case, we have put the colors in a complementary way. We also saw this in the last lecture. So you can organize the colors. So for instance, here we have red, and then here we have cyan. Cyan is the opposite of red. And the sense of opposite is how they excite our neurons. Okay, so we have some sensors for colors, and then the way cyan excites our neurons is the opposite of red. Same for magenta, red, and blue, and yellow. So if I'm shifting just the red channel to the left, what I'm making is more cyan. So this image is now more cyan than it was. Do you have any questions? Just right. Yeah.
It's going to los valores van a ser cuando se vaya a hacer cierres con los valores de gamma más o menos
Eso es.
cuando pedías en el teoría.
Eso. Okay, then original again, and then you apply gamma equal 2 in the green, so you have same effect now in the green channel, and then this arrow here tries to represent that you are moving the image into the more green region, and you apply gamma equals 0.5, and you're moving into the magenta region, and then the green channel is moved towards the origin. And then also with the blue, so this is all the time the same, different colors. Okay, so now, different ways to represent colors. So we have studied one or a couple of them, RGB, CMY, but those are not the only ones. There are also a whole family of other color representations that may decompose. So the idea is that to reach a color, you need three numbers. These three numbers that you have to navigate in the color scheme, so that to reach your point. And you can have three instructions like in the RGB, or you can have a different set of instructions that typically they separate the intensity. So the intensity is how much light I'm receiving. So this red channel is how much red light I'm receiving. But this is how much light in total. I don't care what is the wavelength of those photons, how many photons I'm receiving. And then somehow I will need two other numbers to reach my color. And these two other numbers, in this particular example, they are called A star and B star chroma. And in general, all these compositions are called luminance and chrominance. So you have one channel for the luminance and two channels for the chrominance. So we will see one particular representation of those. This is another one, but you'll see that all the time it is the same idea. So you separate how many photos you are having, and then two numbers for the color. So the way our visual system works, we have the image in real life, and then this project in the eye. In the eye we have RGB sensors, so that is why also RGB is so important for us. So we have chosen RGB not arbitrarily, but because we have RGB sensors. But then in the brain, somehow the three channels are combined into a luminance and then somehow two chrominance layers. But they don't need necessarily, so what we do in the brain doesn't need to be necessarily the mathematics that we present today. But in the brain there is no mathematics, but the way that it works somehow resembles these mathematics that we can see. Okay, so this was the first attempt to organize the colors. It goes to Maxwell, same of Maxwell's equations. And very often, when you do an exam, you confuse Maxwell triangle doesn't have anything to do with the color cube. So these are totally connected. This was the first attempt to try to organize the colors in some place and another way. Okay, so the way we will represent the colors will be this one. We will study one that is called HSV. So HSV is hue, saturation, and value. So the value, we will present them in more detail, but somehow hue and saturation will have to do with an angle, with a vector and the angle that it makes with respect to another vector. So, but the interesting point here is if you have three numbers RGB to reach a point, you also need three pieces of information in any other system to reach another point, the same point. Okay, so let's see. Let's start by studying the color cube. So this is the color cube, the origin is here, so this is the 0, 0, 0. And this is the red axis, this is the green axis, this is the blue axis. So it goes, the origin is here, in this corner. And then we may look for all the points such that they satisfy R plus R plus D plus B equals C. So that is the equation of a plane. Okay? So if it is the equation of a plane, it must be some plane here in this cube. So if you look at it, so for instance, if you say C is equal to 55, just for the sake of example, the equation R plus G plus G plus B equals C equal to 55. So we have chosen C equal to 55. So we know that, and we call that the plane phi. So phi is the set of vectors such that this is complete. Okay, so then we know that C00 belongs to phi, that 0C0 also belongs to phi, and 00C also belongs to phi. We can have any other combinations, so you can have C half, C half, 0, this one belongs to phi, and then you can have, for instance, this one is interesting. This one, C third, C third, C third, also equals C third, also belongs to the same plane, and so on. And this is interesting because this one here is a gray value. You may remember that gray values are those colors that have the same value in the three components, in the three RGB components. So we have 0, 0, 0, we have that, we have 255, 255, 255, you have Y, and then all the numbers in between, we have are gray values going from black to white. So this point is interesting. Actually, this C third is the value. We call this the value. That was the average. Remember, the value was R plus D plus B divided by 3. In this case, the value is C30. Okay, so all these points belong to that plane. And here we have the ones, the corners that we have already highlighted. This is red, green, blue. So this is C00. This one is 0C0. This one is 00C. And we also know that there must be a point somewhere that is C3rd, C3rd, C3rd. That is a gray point. So all these planes, they always contain a gray point that is somehow hidden. And we will see what it is now. Okay, so what it says here is that if C is smaller than 255, then the intersection between the plane and the polar cube is a triangle such as this one. If C is larger than 510, it's also a triangle. But if C is between 255 and 510, then the intersection of the plane and the cube is an hexagon. Okay, so yeah, the conclusion with the Maxwell triangle is that this Maxwell triangle, this one here, is not any one of these intersections. Okay? These triangles are not the Maxwell triangle. Okay, then we may also study, for instance, let's go for one of these sides. Okay, the plane, so there is a plane, this side is also a plane. The intersection of two planes is a line. So which line is that? Okay, so let's see. So we have on one side, we have this plane. We have the plane, let's call it plane 1. This is plane 1. Then we have plane 2. So plane 2 was the side. Okay, what is the equation of that side? This is the side. So what is the equation of all the points here? So all of them, they have the property that the green is 0. So that is the plane. So it is all the points are dB such that G is 0. And this you can also write like this. So any point in that plane, you can represent it this way. 0 to B. Sorry. Okay, so all of them you can represent in this way. And if you have a point that belongs at the same time to this plane and to this plane, then all those points they must satisfy. So the points that we're looking for, they satisfy R plus D plus B is equal to C. The other one is that G is equal to 0. So all those points satisfy R plus B is equal to C. And then you can put it as B is equal to C minus R. And here you have the line. Okay, so let's count degrees of freedom. How many numbers you are free to change here? You are free to change two numbers. So two numbers means you have two dimensions. This is plane. It's a two-dimensional. Okay. Now I have to place. So this is 2D. This is 2D. And the intersection must be 1D. I know that. So this must be 1D. So why do I have only 1 degree of freedom? Because you can change R. G you cannot change because it is fixed. And then once you fix R, B is automatically computed. So B cannot be equal to anything. So if you give me R, I will tell you B. Okay? So you have only 1 degree of freedom. So you know now that the intersection of two planes is a one-dimensional line. And it is a one-dimensional line. In our example, it was the line R plus D equal to 55. So that is the one that is highlighted here. Okay, so we have R plus D equal to 55. And you may wonder, okay, this line, where does it go when R is equal to 0? When R is equal to 0, B has to be, when B is equal to 0, R has to be 255. And when R is 0, B has to be 255. So you are seeing there is this line here. So it is this plane and this line, this diagonal. And then in this diagonal, you are going from perfect blue to perfect red, and then you have a mixture. So far, so good. Okay, good. Okay, what if my C is larger than 255 and smaller than 510? Then I will have this case. So I have a plane, and this plane is intersecting the cube in this hexagon. Okay, the hexagon doesn't need to be regular, so you can have an irregular hexagon, so with different sides, lengths of the sides. And then, for instance, this is another example. So if I look again how this plane is intersecting this side, then now this is the intersection. So it is another line, but it is a different line. We have chosen C383. Okay, good. Then you may look at any other intersection. So, for instance, this is the intersection with the green equal to 55. So this plane was green equal 0. This plane is green equal to 55, and then you may look at what is the intersection of the plane with that side of the cube. Okay, so this is the intersection of the side of the cube. You have to be careful always with where the origin is. So here, the origin, this is R equals 0, this is blue equals 0, so the 0, 0 is here. So it has been drawn in a way that the 0, 0 is there. Okay, then, yeah, you have all kind of intersections, all kind of things. Green equals 0, green equal to 55, red equal to 55, so you can look at all possible intersections. And then you may also see how this intersection. So if you look at, this is the color cube, this is solid somehow, we don't see the inside. And then when you remove everything down to the plane, this is the intersection. And then what we will see is that this middle point here is a gray point. Okay, so now we will start constructing our HSV representation of colors. So this HSV is, okay, so if you want to have a color, you have to give me 3 numbers in the RGB space. So an coordinate system, so you tell me 3 instructions to reach that point. But I can also tell you 3 instructions in a very different way. So this point will belong to one particular plane, that is of the form R plus B plus B equals something. Okay, this point will always belong to that kind of plane. Okay, so I have to look for this equals something is simply the sum of the 3. So there is a plane that contains that point and that is perpendicular to the 1, 1, 1 direction. So if you remember, go again to the algebra. So let's say I will do it with x, y, z that we are more familiar with. Okay, so you have x, y, z, and you have a plane here. This plane is characterized by a vector that is perpendicular to it. I call that vector u. And there is a distance, green. That distance is the distance from the origin to the point where one of the points of the plane, in the direction of u. Okay, so you may remember that these, you can write it in this way. Say the equation of that plane is u times r equals v equals, we will put a name before the distance. Let's say that the distance is v. This is the equation of that plane. You may write it in this way. I will use actually find ux times x plus uy times y plus uz times z equals v. So if you have a plane that is of the form x plus y plus z equal v, actually this is the same as 1, 1, 1 times x, y, z equals v. So your u vector is the 1, 1, 1. So that plane that you are drawing is perpendicular to the vector 1, 1, 1. If you want to make it unified, you simply divide by the norm of u. So you can also write 1 over. So now this vector has unit norm. And it is exactly the same thing. It is exactly the same thing.
Una pregunta.
Venga.
O sea, el D es parte de 0, hasta como el plano perpendicular. Luego, la U sobresale del plano.
Eso es. De hecho, aquí es un colapso. Porque si aquí divido por ahí del vector, aquí también debería dividir por ahí. Por no complicar un detalle. Vale. So that is a plane that contains your color. And you may look for, okay, this plane, and I have the 1, 1, 1 vector. The one, so I have the 1, 1, 1 vector. So this vector, if you prolong it, you will reach the plane at some point. At this point, because it is 1, 1, 1, and it also belongs to the plane r plus a plus b equals something, this will be a great value. Do you agree with that? Because it belongs to this line. So if it belongs to this line, r and g and b are the same, because it belongs to the 1, 1, 1 vector, to the 1, 1, 1 direction. So r is equal g is equal b, and it belongs to this. So it must be that actually, if you remember, this was the value, this was the definition of the value. So this point is the point BBB. So if this is the value, then this is the point BBB. Okay, that is what is said here. So that point is, this is B, and then you have it in the 3-axis. Okay, so now I have given you one piece of information how to reach that, your color. Let's look for the second one. The second one is how far your color is from the BBB point. Okay, so I will call that the saturation. So if your point is very close to the BBB, then I will say it is very little saturated. And if it is very far, I will say that it is very much saturated. So it is the distance between your color and the BBB point. Okay, so now if I tell you the distance, you know that it is in this plane, your color is in this plane. I have told you the distance, but then there is a circle of points that all of them are at the same distance. So I have to tell you which one of the points in the circle. So one possible way is, okay, that is a direction that is uniquely defined in that plane. That is, in that plane, you will have a point that is maximally red, that is only red. That is this point here in the corner. So the point, the vector going from BBB to the red point, and the red point is called here, what is it called? Yeah, this one. Doesn't have a name. This point. Okay, this point is this one. So that is this vector. And there is a vector that goes from the BBB point to your color. And then you have two vectors. And if you have two vectors, you can define an angle. So it is the angle between those two vectors. And then that is the hue. The hue in Spanish is tonalidad. So it is doesn't say too much. We don't know exactly what tonalidad is. But here we have a precise definition of what it is. That is the angle between the maximally red vector, so the vector that goes from the gray to the maximally red, and then your color. So now I have the three pieces of information. The first one is what is the center of that plane. That is the BBB. And I will tell you the module of that, because the three numbers are the same, so I just need to tell you one of the numbers. And I will tell you how far you are from that point, that is the saturation. And then I will tell you the angle that your vector, your difference, what is the angle between your difference and this maximally red vector that goes from the gray to the red. And this is the way to formalize that. So, okay, so this point here, this point is B, 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 B. Okay, good. Then S0. S0 is the difference between your color and the gray point. Okay, so this is another vector, it is well defined. And then this point here, we haven't given a name by this thing. Sorry. So we have given this this calculation. We don't have a name for it. And the vector that goes from the gray to this one is this one. So it is where you want to reach, where you start from. So this is this vector. And then the angle between these two, that is the view. So you started with 3 pieces of information to reach your color. And now you have 3 pieces of information to reach your color. But this was in a Cartesian coordinate system. This is in a somehow kind of polar coordinate system. So I'm telling you which is the plane, within that plane I'm telling you the radius and an angle that is polar representation. So yeah, the main idea here is that you are not restricted to give colors in only one way. So RGB is one way, CMI is another way. Both are based on Cartesian vector, not Cartesian coordinate system. But you can also give it in polar coordinates. But the important thing is, if you need 3 numbers in one Cartesian system, you also will need 3 numbers in any other representation, any one. You also need 3. And the value is the one of luminance, intensity, whatever. So that it doesn't care what the intensity, where the intensity is coming from. I don't care if it is red, green, or blue. I will mix the 3 of them. So it is somehow what I was mentioning here. But what we see, we combine all the photons into a single channel. That is intensity or luminance or however you want to call it. And then you need 2 numbers for the color. So it has the same spirit as the one that is operating in our phase. Then, yeah. Okay, so some nice representations of these things. So now the origin is here, 0, 0, 0. We have this plane. We want to represent that color. Then that is the color we want to represent. Color, and then we have the 1, 1, 1 line. And this line will intersect the plane containing our color at one particular point. That will be the V vector. And then you can compute ds, that is the difference between the gray color and your color. And then we have the vector V, the rest. We have the maximally red point in that plane, that is this one. And then you have also this blue vector here. And then you have the angle that goes from the blue to your color. So now I have given you again 3 pieces of information to reach your point, but these 3 pieces are somehow more complex than the RGB. So yeah, this is all the time different representations of that. Okay, then we have these planes that we have been talking about. How do they look like? So this is the RGB space. Here are the sides of the cube. And now we will make R plus B plus B equals C. So we will increase C. So at the beginning we have a very small C of value. So we have a very small value. So we have the intersection is down there almost in the corner. Right? It's a very black triangle. We barely see any color in there. And then we increase B, we are increasing B all the time. And now we see the colors. So the first triangle also had colors, but they were already dark, so we could see them. So all these intersections are triangles, and at some point you start C is larger than 155. Then you have an exact count. Here you have actually you have more than 6 sides. No? You have 1, 2, 3, 4, 5, 6, 7. So it is an exact. The intersection is an exact. The best way to look at it is here. Here it is somehow confusing because you also have the signs here. It's more clear. And it doesn't need to be a regular hexagon. This is an hexagon, but it is not regular. Okay, and then you have triangles again, but now they are rewrite. Okay, good. Any question after here? No? Okay, so let's make a break. So let's see this RGB conversion again. So we have seen how to go from RGB to HSB. There is a recipe for doing that. So first you compute C. So you give me an RGB point, and from the RGB point I will compute C. And then I will compute the V0 vector, that is simply 1/3 CCC. And then I will compute the module of this vector. The module of that vector is this one. V0. That is not the module is this. So it is C divided by the square root of 3. And we have defined at the beginning, in the first lecture, we defined the value in this way. And now with this vector, it is C divided by the square root of 3. So it is an extra square root multiplication here. Okay, so we have the module of V, and then we define the vector S, that is, so V0 will be our new coordinate or origin of the coordinate system. So you have your point, and then you want to express with respect to the new origin, so you have to subtract the origin. And then that is the distance vector, and then you can compute the module of the distance vector. So again, the summary of the recipe. You start with a point, compute C, make some calculations, and again you have V0 and S0, so I have given two pieces. And the last piece is this one. So we will compute, this is the maximally read vector, and we have put the name there, that is R. So again, R in the new coordinate system. So in the new coordinate system, you have to subtract the origin. So you subtract the origin, and then you have X. So I call it T, here it is called X. And then you measure the angle between X and 0. And the angle you measure in this way. So you compute the inner product between the two, divided by the norm of the two vectors, and this is the arc cosine. Okay, good. Then, yeah. So, what is the shape of X? Okay, so what is the maximally red point? It has the coordinate C00 because it is red, and it has to belong to that plane that is R plus C plus B equals C. So it has to be C00. And then V naught was CCC divided by 3. So this X is this thing. Got it? So this is the maximally red point. Maximally red point because it belongs to the plane R plus T plus B equals C. It has to be C00. And then V naught was CCC divided by 3. And if you subtract these two, it's equal to N. Porque sería 3C menos un tercio, o sea, C menos un tercio de C, pues 2 tercios de C. Okay, so now we have X. So again, the recipe now is very simple. So you start with P0, then you compute C, you compute V0, then this is C. Then you compute the module of S. This is the module of S. And X you have in the previous slide. X is this one. And then you compute the inner product of S0 with X divided by the modules, and then R cosine of that. So now you know how to go from RGB to HSV. And yeah, this is too technical, we'll skip it. That is that it is custom to, instead of reporting S, so the saturation, you can compute what is the maximum saturation I can ever find, and this is the maximum saturation. And then instead of reporting S0, you report S0 divided by S max. So it is normalized between 0 and 1. But this is too detailed. And then there are some other special considerations. What happens if this is 0 divided by 0? Those are too detailed. Okay, so now let's go in the opposite direction. So now you're an HSV point and you want to go to the RGB. So how to do that? So you have to find, actually this is a change of coordinate system. So you can define a new coordinate system that is attached to the plane that we are interested in. So this plane that is perpendicular to 1, 1, 1. Okay, so we will define 3 axes. So this one that will be called X, the perpendicular one that will be called B, and Y is simply the multiplication of these 2. You may remember this from your standard algebra. That is, we have 3 vectors like this. We have X, Y, Z. You know that X times Y is equal to Z. Then Y times X, Y times Z is equal to X. And then, what else? Z times X. You are shifting all the time 1 to the left. So shift this one is easy to remember. If you shift it to the left, you have Y times Z is equal to X. You shift it to the left, Z times X is equal to Y. So that means that once you have 2 vectors of a coordinate system, you can compute the third one by this outer product. So if you give me X and B, but we have reason of how to compute them, then you can simply compute Y as B times X. Okay, then in the XYV coordinate system, what are the coordinates, what are the directions of XYV? Is in that coordinate system, which is the standard 1, 0, 0, 0, 1, 0, 0, 0, 1, in that coordinate system. But we want to find the correspondence between this coordinate system and the Cartesian RGB coordinate system. That is what we will do now. Okay, so to do that, just a reminder of how this point was constructed. So it is in the plane, so it is contained in this plane. And so if it is contained in that plane, the V will be equal to 0. That is, how much you have to travel in the direction V. You don't have to travel. So you stay there. Okay, good. Then you have this coordinate that was kind of polar representation. So the hue was the angle, the saturation was the radius. So in the XYV coordinate system, that point has this coordinate, S cosine H, S sine H, and then 0. But that is in this coordinate system. And this is the notation you may remember of coordinates in this coordinate system. Okay, so another way to write that would be this coefficient times X plus this coefficient times Y plus 0 times V. Okay, that is in the coordinate system XYV. So now we want it in the RGB. So you have to convert the X and Y into RGB representation. Okay, so let's look for that. Okay, so yeah, so this is to say that you may have the same color, the color is S, in two different coordinate systems. In the RGB, it has this representation. In the XYB, it has this representation. And what we want to find is, okay, what is the RCA, B0, B0? We want to find those from this question. And to do that, we will convert each one of the, okay, so let's, you may remember this thing. So when you have a change of coordinate system, you have a change coordinate system. So let's say that I have, I don't know, yeah. I have here point. So I have here point. This is my point. But I have a different coordinate system. That is this one. This X prime, Y prime, Z prime. And these are vectors. So you have P, you have this color. So I have the coordinates of P in the X, Y scale. And also you have the coordinates of P. You have the coordinates of P. And now in the prime system, X prime, Y prime, Z prime. And these are not the same. Okay, so what is the, there is a relationship between the two. So there is a relationship. So I can use one of them to compute the other. So I have the X, Y, colors are nice, but it is also very to write. So I have an X, prime, Y, prime, Z prime. And that must be a matrix A that transforms them. And this matrix, the columns of this matrix, will be X prime is expressed in the XY set, and then Y prime expressed in the XY set, and Z prime expressed in the XY set. XY set. So the columns of this matrix are the coordinates of the unit vectors in the XY prime coordinate system, expressed in the original one. You remember this one, Oliver? Okay. So when you have two coordinate systems, you can express it, and you know the expression in one of them. You simply multiply by a matrix, and then you have it in the other coordinate system. You remember that? So what we will do now is to compute this coordinates. So we will look for these things. For this, for this, for that. Okay, so this is what so this applies. This matrix transforms any point in the XYB in the RGB. So in particular, it will transform X prime. So X, Y, B has some representation in the RGB. So let's see which one is close. Okay, so this is the same I was saying. Okay, so let's B is very easy because B is the unit vector that is going along 1, 1, 1. That this is the unit vector. Okay, so B is very easy. X is not so easy, but we have it there. So we have it here. So what is the unit vector that goes in this direction? This was the direction. So what is the unit vector? So you compute the module of that, divide, and then you have it. And it is this one. It's this one. Okay. So that is the unit vector going in the direction of x. And now we have b and x, so you have y. So you simply have to multiply the two. And this is the multiplication. So now we have the x, y, b coordinate system vectors in the RGB coordinate system. Then we have the matrix, and we have everything. We simply have to multiply. So this is the matrix. So if you want to go from HSB to RGB, you have to take the coordinates in the HSB. So this was the coordinate in H, this was the coordinate HSB. So X, Y, B. So this was the coordinates, and now you have to multiply by this matrix. That's very easy. So then your color is this one. So if you're HSV, this is the transformation. So you have H, you have S, and then you have to add this here. So good. After here. Okay, so then let's consider one of these hexagons. Okay, so we take this hexagon, that is the one of R plus C plus B equal 384. Can be composed in 3 channels, red, green, and blue. And here, for instance, the maximally red green point is this one. So this is very intense. This is very dark. This is the maximally red point. Maximally red is here. Maximally green is here. They are not in the corner. This is maximally blue. So yeah. Good. So it is the 3-channel decomposition of the hexagon. And now we can decompose it in HSB. Okay, so now the value, all these points in the hexagon, they all have the same value. The same V in your representation. All those colors have the same, because they belong to the same plane. Then saturation was how far you were from the middle of the plane, so from the gray point. So the gray point is here. So how far you are from the gray point. So here you are pretty close, here you are pretty far. And then you have the angle. So what is your angle between the maximally red and the color? So let's say that your color is here. So if your color is there, then you have a very little angle. This is the maximally red color. And then you have a very little angle. And then as you go in this direction, you have a higher and higher angle. Okay, so now you have the hexagon. You can decompose it in RGB, but you can also decompose it in HSB. And now you understand this representation. And you can put colors to the hue. Okay, so now we can play with the Do you remember that we were taking this image and changing the colors in the RGB? So we can do now the same in the HSV. Okay, so you take the image, you transform it into the HSV, you increase the saturation by 50%, so you multiply all the saturations by 1.5, and then you transform it back to the image. So now you see that, especially when you look at the screen, or this one, but when you go from the original to the more saturated, you see the saturation. So these colors are saturated. And then you can decrease the saturation, so you may multiply by 0.5 instead of by 1.5. Now let's change the hues. Okay, so now this is the original. And I think here, but let's put it there. Okay, so what we will do, you have a color, let's say this color is here, you have some angle. And now you will take that angle, so let's make it red. So you take that angle and you add 60 degrees, for instance. So all the reds, they will become yellow. And all the yellow, they will become green. And all the green, they will become cyan, and so on. So this is what is represented here. All the reds will become yellow, all the yellow, they will become green, and so on. So if you take all the angles, shift them by 60 degrees, then you're making this transformation. You may turn it 120 degrees, 180 degrees. This is the opposite, this is the negative. So you have, and now you understand why we said at the beginning, at some point, that cyan is the opposite of red. So cyan is the opposite in the sense that you have to turn 180 degrees to read cyan. And yellow is the opposite of blue. So now you have the opposite image. So you turn your colors by 180 degrees, you have the kind of negative of the image. 140, 300, and 360, that is the same. And this is some nice representation of the histogram about the simple. So we can, instead of angles, we can put names of those angles. So this is 0, this is 60, this is 120. And then you compute what is the histogram of the saturate of the hue of that image. And then as you are adding the degrees, what you see is that the whole histogram is shifting to the right. So it's turning 60 degrees against that. Okay. Good so far? Yeah. So different way of representing colors. Good. Now, let's say that I think it is better to introduce it this way. So let's say that you are given like you are given this image. So this image was printed in a photograph, but the photograph is 50 years old. Now the photograph paper has degraded. So you know that the natural colors were like this, but this is the photograph that I have. So can you correct those colors, transforming them into these ones? Okay, so we are looking for color transformations of a different kind. Okay, so let's see how to do that. Okay, so instead of going from the age to the original, we will understand how to go from the original to the age. So the color is just an RGB. Good. Then I can find transformations that make the image more red, more yellow, more green, more cyan. One family of transformations is matrix transformations. So Or you can transform your colors in any way you like. You may do a gamma transformation, as we have seen, and you may apply different gammas to different channels. But you may also do a matrix transformation, like this one. So it is simply, you give me a color, I will do something on that color, and I will give you another color. And what I do can be linear, a linear transformation, or it can be a non-linear transformation. So you can put any function that takes a vector, produces another vector. So let's study these kind of families, or this family of linear transformations. So let's say that my matrix is very simple. It's just this one. So it is G and B are attached, but R0, so the red, is multiplied by this scalar, so that it becomes R1. So let's say that my scalar is 175 divided by 125, I don't know, 1.3. So let's say that my scalar is 1.3. So when I multiply anything, this vector here by this one, it becomes this one. And green and blue have not changed, but red has. So it is, what is the red? Yeah, here. So it is, I have this vector at the beginning, and then you multiply just the red. So you are transforming, you are moving up your red color, any color more to the red. So if you have this purple, it would be a more red vector. And you can do the same in all the axes. Okay? You can do that in green, so now this will become more green. You can do it in the blue, so now this will become more blue. So you can do it very simple scalar transformations. You can combine the three of them. And in general, you will have a matrix. Okay, so instead of just having 1.3, 1, 1, and then all the rest to 0, you can have any arbitrary matrix. So you take any color, multiply by this matrix, you will have any color. And yeah, this is what is represented here. Okay, so you take any color, multiply, and you get any color. And this is interesting. So we have a couple of images. So we have a couple of images. We go to I, J. So J at the position R, I at the position R is an RGB. Then if my transformation is this one, it will also be an RGB. So let's call this I, DI. So this will be now RJ, G. Okay. Okay, so we have G, J, J. So we are taking this one. We are multiplying by A and we are getting something. So red, let's make this image green. So this is green and this is green. So this is our transformation. So if I want to go from I to A, I have to multiply by A. What if I to do the opposite. I go from J to I. You have to multiply by A minus 1. So it is simply solving this one. So you solve for I again. It's A minus 1 times J. Okay, so A goes in one direction, A minus 1 goes in the other direction. So that is why A minus 1 is not present to compute. Okay, so now let's say that you are given pairs of colors that correspond. So here let's go to example. So let's say that you say, you know, this color in the age photograph should be this one. You see that red and green are almost the same, but the blue is much bigger now. Okay, so what has happened is that the blue has gone down. Then you take another color and you say, okay, you know, this one should be this one. Okay, so now the blue has gone up. No, sorry, it has gone down. It has gone down from the original to the age. You are given another one. So let's say that you are given three colors. Okay, so we are given three colors. Let's count how many equations we have. So let's say that you are given one pair. Let's say that you know that I color 1, I blue, I1. This is one of the colors in the original. Is transformed into RJ1, green J1, blue J1. And you have the same for two other colors. Okay, for 2, 1, or 3. Let's count. Okay, so this is A11, A12, A13. This is A21. This is A21, A22, A23, A31, A33, times this thing, times. Let's remove this implies. Let's put equal RJ1, green J1, blue J1. So now, this is R, it might be this way. A11 RJ1 plus A12 J1 plus A13 A13 blue J1. And this multiplication, this one has to be this. Perfect. And the same for the other side. It's amazing, right? Then, now I can rearrange. So, how many unknowns you have? Which are your unknowns? Yes. These are our unknowns. We have 9 unknowns. How many equations I have? So, the green is 1. one equation. The other two, they are giving me two equations, two extra equations. So I have three equations and 9 unknowns. So if you give me three colors, like this one, 1, 2, 3. There is only one A that transforms one into the other. Only one. Okay, and you may find it in this way. So another way to write this equation is in this way. So I can write R. Let me call it for not making it confusing. This is color 1. Color 1. Sorry. Color 1 in I. That is a color. You multiply by A. And it gives you. So you multiply the color J by A, and it gives you color 1 in I, and color 2 in J gives color 2 in I. Color 3 in J gives you color 3 in I. This is I. This is I. And these are color vectors. Okay, so this is the RGB. So now let's count dimensions. Okay, so this is RGB. So it is 3 on this side. And this is 3. This is a 3 times 3 matrix 2. And this is again 3 because of the RGB and 3. So it is 3 times 3 A. So let's call this matrix. Be more consistent in the notations. This is color I matrix. This is color A matrix. The sizes are 3 times 3 times 3, 3 times 3, 3 times 3. So I can solve for A by simply inverting this one. So I can say A is Ci times Cj minus 1 equal A. Yes. So this is one nice way of solving for A. And then we have A. Okay, very good. You give me three colors or three color pairs. 3 color pairs are giving me 9 equations. I have 9 unknowns and I can solve for it. Very good. Now you're very kind. You give me 4th color. Let's look at the sizes now. So this is 3. So let's write the equation that we have. We have Ci is equal to A Cj. But because you are so kind, you give me 4 colors. So now this is 3 times 4. This is 3 times 3. And this is 3 times 4 again. Which makes sense. The multiplication makes sense. And I compute Cj minus 1. No. Why not? Because the inverse is only defined for a square matrix. So you cannot. So you have more colors, you have more information, now you cannot use them. And the thing is that if you have 9 equations and 9 unknowns, there is only one solution. But if you have 4 color pairs, and you have 12 equations and 9 unknowns, so it is very unlikely that you will find an exact matrix that gives you exactly the 4 colors. Now let's try to reformulate the problem, and then we will say, okay, now I have 12 equations, only 9 unknowns. So I cannot fully satisfy all of those. Okay, let's see the best I can do. So the best I can do is, okay, so let's say that I have all the colors. So the sum over all the colors, of I have color I, this is a vector. I have the transform one. The transform one is this one. Okay. So these are vectors. And ideally, I can let's say that all the colors are consistent. So if all the color pairs are consistent, then I will find a name such that they transform this one, and I have exact XCI for all the colors in your pairs. But let's say that they're inconsistent. So if they're inconsistent, these two vectors will not be the same. So I can compare, okay, how far are they from each other? So this is the distance between the two vectors. Clearly. So if that is the distance between the two vectors, what I can try is to try to find the A that minimizes this. So it doesn't satisfy all of them very accurately, but they somehow satisfy all of them more or less. And this is squares. We are computing so the squares of the vector, and this is list. We are trying to find the minimum. This technique is for these squares. So you try to find the matrix that better satisfy all of them. You can also formulate this in this way. So now here we have two vectors. Now I will use these matrices. So what you want is the minimum of this node. CI minus A, C, J. Now these are matrices. This is called the Frobenius. This F comes from Frobenius. Okay, now the solution is in the slides, but I will give you an easy way to calculate the solutions. And this solution, I think the nice thing about it is that it makes you think about matrices in a very nice way. Okay, so let's start with this. We want CI, this is a matrix, to be approximately equal to A, C, J. Okay, we have the sizes. Let's say that we have 3 pairs. We have P pairs. Okay, so we have many pairs. So this is 3 times P, this is 3 times 3, and this is 3 times P. And we have said we can compare that. Okay, so now let's do something. That is, we will multiply on the right by CJ transpose. I have CI times CJ transpose. This is equal to A, CJ transpose. Now let's look at the sizes again. So the size of this thing, this is 3 times P. Si no rápido, no sigue. Tenemos rápido P times 3. And this is 3 times 3. And then this is 3 times P. And this is P times 3. So now we can group them. This product is 3 times 3. 3 matrix we can invert because it is a square. So we invert that thing, multiply by the right by that. Then we have CI, CJ transpose multiplied by CJ multiply CJ transpose minus 1. This is it. And it turns out this is the this A is the one that minimizes this. So this is the matrix that minimizes this. The least square solution of this problem is this one. So simply reasoning on the sizes that we have involved, we have come to the solution of a relatively complicated problem. And this thing here, look at the structure of this two. So here we have inverse. This is inverse. So we have a square matrix. We have the inverse. All this thing here is called the pseudo inverse. Pseudo inverse. Actually, it has a very nice name. More than rows. Those are the two guys that made this. Penrose was Nobel Prize. Okay, by the way, do you know the Nobel Prize of this year? No, physics and chemistry. No. They went to artificial intelligence and physics and application of artificial intelligence to chemistry in chemistry. Yeah. So very nice stuff. This is what is explained here in the slide. Okay, we have done. So they are pairs, and then we want to minimize that.
So, los unknowns, la A,
Sí,
es lo que intentamos averiguar de cuando pasa de la original a la otra.
eso es.
Como los números que hacen que cambie.
Eso es. Y una vez que sabes cómo degradarla, puedes corregir.
Vale.
So if the number of pairs is equal to 3, then you have the inverse. But if it is more than 3, then you have to do the pseudo inverse. So you have the same kind of. So now let's do it here. So if you use so we have 4 pairs. And then if you use just 3 of them, this is what you get. So this was the 8. You use 3 pairs of those, the first 3, and then this is the correct identity. Now you use the 4 pairs. So this is original, this is corrected. Now you use 4 pairs, and this much better. So these least squares does not satisfy all the pairs at the same time. Right? This is really much better work. And this is how to do it. Okay. Any question? Bueno, hacemos un descanso de 10 minutos hasta 20:22. Y